Hello everyone, we're going to discuss problem number 29 in your book on page 334. We did this problem in class today. It was right towards the end of class. The bell rang and we didn't quite finish it completely. We did, but very quickly. And I wanted to go over it again, and I'm going to show you a shorter way of doing it, the shorter way than what we did in class. In class, I went crazy with this and I made this problem very, very long. And I'm going to show you how to make this much, much easier. Okay? So the first thing I'm going to do here is notice that these radicals are all cube roots. Okay? And anytime my radicals have the same root, I can simplify this a little bit. In the denominator, when I have a root times a same root, I can join these radicands together by the radical product property. The radical product property says that if you have the nth root of A times the nth root of B, and what this means is this is one number, this is another number, but the indexes here, or the roots, are both n. That means they have the same number here. That is the same thing as having the nth root of A times B. So what this property tells me is that I can take these radicands as long as I'm multiplying roots, and I can join them together in multiplication underneath the same root. And I'm going to use that here in the denominator. So this will be equal to the cubed root of 54 over the cubed root of 32 times negative 4. And that's all I did. I joined the radicands because I have the same roots. And the same thing, we have a property that's the quotient property of radicals that tells me that if I have the nth root of A divided by the nth root of B, then I can join them underneath the same radical. Okay? So I'm going to join these two radicals into one big radical because they have the same root. So this will be 54 over 32 times negative 4. And now what I've achieved here with this is that I can cancel out common factors. So I'm going to cancel out common factors with 54 and 32. I can divide 54 divided by 2, that gives you 2, and 32 divided by 2, that gives you 16. And I can't cancel out anything else. 54 divided by 2 is 27. Sorry for that. Okay, 54 divided by 2, 27, and 32 divided by 2, 16. So now this is what I have. I have the cubed root of 27 in the numerator, and in the denominator, I'm left with 16 times negative 4. All inside the cubed root. Now that equals the cubed root of 27 over 16 times negative 4, that's negative 64. And now I'm lucky, 27 is a perfect cube. What number do I multiply by that same number 3 times and I get 27? The answer is 3. 3 is the cubed root of 27 because 3 times 3 times 3 is 27. And the same goes for my denominator. Is this a cubed root? Yes, it is. What number do I multiply by the same number 3 times and get 64? Or negative 64, I'm sorry. So that number would be 4. 4 times 4 is 16 times 4 is 64. If I multiply negative 4 times negative 4 times negative 4, I get negative 64. So negative 4 is the cubed root of negative 64. And here's your answer. Your answer is negative 3/4. if you don't know that the cubed root of 64 is 4, this is what you can do. Now, we're done with this problem, but I'm going to show you another route if you don't know the cubed root of 64. And I'm going to write that in another color. I could have done this. I could have written the cubed root of 27, and I could have written 64 as negative 8 times 8. Now you know that the cubed root of 8 is 2. And then this would have given you the cubed root of 27, 3. And then the cubed root of negative 8, that be negative 2, times the cubed root of positive 8, which is 2. And then this would have given you negative 4 in the bottom, negative 3/4. Okay? There you go. So if you don't know the cube root of something, try breaking it up into two numbers, and at least one of them being a perfect cube. Okay? So you can go this way, or we can go this way. Whatever's more comfortable for you. I hope you understood this example. It's much, much easier than what we saw in class. I'm sorry about that. So hopefully you'll watch this video. I'll see you in the next video. I'm going to do another example from the book.